A very good day to you around the world. I see we have participants ranging from California towards Europe and even Asia. And I'm trying now to share my screen in hope you can see it now. Okay, here we go. Okay, perfect. So again, very good day to you. And today we are talking about alloy selection. I'm very happy to be invited here by Dr. Valerie Bauer and the Connector Library. And we have planned to talk today about alloy selection, which is sometimes the easy topic, sometimes a pretty difficult topic, because it depends very much on applications. So I will provide a small introduction. Then we go into application profiles. I will explain you about alloy maps and especially the Boway alloy maps. And I will give you later an example of design to cost, because as we all know, currently all around the world, companies are under cost pressure and what can be done there and in a small summary. We will make this session today. I will present, and please note your questions you may have. We will later have a Q&A session afterwards where you can highlight your questions. And in general, my presentation will be shared here to the Connector Library, so you will be able to access this later on, so for your own documentation. Okay, my introduction starting first with the copper tree. So giving you an idea about all the different elements you might be able to, let's say, add to copper. And as such, as in a tree, you see a lot of branches. And typically, when we look into the connector area, we see it dominated by just low alloyed copper. So that's the orange one. Or if it is brass or if it is bronze. And if we look to the high performance materials, we would find this as well in this orange part. If we look to designations of materials, there are for sure, each region has its own designation, but meanwhile, around the globe, the ASTM unified numbering system seems to be the leading one. So this is as well the way why at Boway we are selecting our alloy names according to the CDA numbers. So this is a big range of numbers. And if I just take a group out of it, let's say the copper nickel silicon alloys, this might start then with a 1 or with a 7 or with a 6. So therefore, don't be surprised if you see these numbers and still talk about a copper nickel silicon. If we look to relevant standards international, I have summarized this here into one slide. And I recommend all over the world to look a little bit into the European ones, EN. Because they are the ones, especially with DEN 1654, a direct specification or a standard on springs for and connectors. And in addition, I have highlighted here as well in orange the one for hot dip tin strips, because the tin coating for sure is a major part of it, which we are finding especially in the area of automotive. For sure, if we go to low contact force applications, as we will find in mobile phones, as an example, we will have gold on the surface, which is not covered in this area. If we look to the US, the dominating specification or standard will be the ASTM B888, which has well a very detailed specification on the manufacture of electrical connectors and spring contacts. I have added as well typical Japanese one. However, so far it seems there is not a specific one on connectors. One thing I would, however, like to highlight to you, if you take, for example, a bronze material, a bronze 4, and we see, let's say, a temper, typically in ASTM may be called half hard, or in EN it would be R480, you can notice that even with the same chemistry, the tempers may differ. So I just would like to warn you a little bit on this aspect. When you specify something, keep in mind this is not internationally standardized. As such, it is not a wonder that typically in connector companies we find that each company has its own connector specification. However, still worth having a look into the standards because we don't want to over-specify, typically just cost money, and under-specifying we don't want to do as well. Okay, good. Let's start now with the application profiles. And this should give you an idea about what are the requirements on terminals for connectors. So in general, we have to understand the terminals, so the metallic contact parts are the ones, which have to ensure the electrical connection between, the one or several contact parts. And if we look to the requirements, in the first place, we see, power, heat dissipation. I think this is a no-brainer. Then we talk about the conductivity, if it's either electrical or thermal. But if we look already to the contact force, many companies or many people think they would specify this by this tensile test. That's okay, tensile test, but not the tensile strength. Typically, you would like to look to the point where the material is going to flow between elastically and plastically. So something close to it, and the most common would be the yield strength. Or another point could be the spring bending limit, which is a, let's say, definable value you see in the relay industry, and we find it in Germany as well in Japan. Then if we talk about, small displacements, you want to have something stiff, we would look into Young's modulus. It could be either high or low, especially when you want to store later on, contact force, let's say in a press fit. You might like to tweak a little bit with this, and these are as well aspects we can think on the material side. In general, if you are bending materials, I think it's very clear, 90-degree or 180-degree R over T is a point. But one of the very key points we always have to keep in mind is, having this contact force over time. And the key word for this is stress relaxation. So we want to have a low stress relaxation. And especially in automotive, this is the one driving materials towards high performance. So when we think about lower cost materials, a point where we always have to keep an eye on. Last not least, why do I do plating at all? So I want to have a persistent electrical performance, so even under temperature and humidity. So how can I plate? How well can I plate? These are all aspects when selecting an alloy, because it's not the same if you take a brass or if you take a chromium-containing alloy or a copper nickel silicon. So just to make a small little summary of what the different applications, from automotive to telecom to computer, white goods, and so on, you see here the typical alloys and the typical focus. So as just mentioned, for automotive, key is relaxation, and then we look to formability. And as such, we see a lot of high performance materials just on the very, very low end, sometimes a little brass. But overall, in addition, this market is as well dominated in the signal market by tin coatings, whereas e-mobility is dominated by silver. And the market share for silver and gold Ls is smaller, much smaller than the tin one. Tin is, you can say, the lower cost version. If we go to telecommunication, this is typically driven by militarization, and as such, we find a lot of, you can say, high strength alloys up to copper titanium, and we find more or less, depending on contact force, the item being driven, for example, by gold. Computer would be similar. White goods, they don't have such high requirements. It's more like tin and silver, and everything like this we will cover now later on in this graphs. So let's start here with the automotive signal contact. And we look to the left side, so that would be, let's say, the female part. And if we look to the graph, you see the most dominant would be the relaxation. We have today applications ranging up to 180. If you have a typical 0.64 millimeter contact, maybe 125. And then as signal, the conductivity is not as demanding, but probably the bending and the mechanical properties plus the plating properties. As such, we find quite a lot of group of materials ranging from copper nickel silicon to copper chromium, copper chrome zirconium, or other copper, chromium, titanium materials. If we go to the male part, we look to the pin now, or to the knife, however you call it. Here we see quite different kind of alloys. Here 14415, that's a copper tin 015, is pretty dominating, but sometimes even other materials. But this is a material I would like to highlight to you, the 14415. If we are moving now to automotive power terminals, you can see here two pictures. One is, you can say, a rather large contact, with a big body and a spring inside. And if we think about the spring, we can go back to the signal properties. But if you go to the body, this is using a lot of copper, and as such, it must be something which can be done even in these thick gauges, which is required. And especially due to the weight, the cost item is extremely important. Else, this is driven by conductivity and much less by the strength or formability. So sometimes in the contact zones, we even find here, due to the high current, temperatures up to 200 degrees C. Again, relaxation is the key then for the inner spring. If we go to other applications, let's think about computer consumer communication, what we find in a mobile phone, from a USB-C towards, let's say, a socket, as we find in servers or in PCs. These are very much applications driven by very miniaturized parts. So the handheld device is driven by miniaturization. As such, the overall key point is, can you produce it in such thin gauge? As an example, a socket going down to 40 micron, 50 micron, or can you actually get the material to such high strength? We are even talking today about strength levels we achieve with copper titanium from Boway up to 1,500 megapascal. So as such, the alloys ranging from the low end bronze towards, you can say, copper titanium, everything inside we find, and Boway is indeed a company focusing on these high performance materials. If we go to press fit applications, as well, something we see revolutionary in the automotive industry, where actually a pin, it could be just a normal pin, or it could be something with a spring, an eye of the needle, or even with something coining, is connecting directly into a metallized hole and with very high spring forces. And here again, the key points are relaxation, the mechanical strength you have, how stiff you can make the spring, or how soft you want it in order to have the right insertion and withdrawal forces. And one aspect as well I would like to mention, don't use the hardest temper for these materials, because typically you need to have some kind of elasticity when pressing in. Another point, because you are contacting directly on the stamped edge, you need to have a material, or it is recommendable to have a material with a smooth stamping edge. So this could be achieved, for example, with a certain microstructure. And here, especially bronze materials are, you can say, dominating a bit, because with natural hard materials, we can influence the microstructure quite nicely. So as such, the materials again ranging from bronze towards the high performance materials, depending as well on what kind of conductivity level or strength level you require. If we go to the white goods, that's, let's say, much more driven, you can say, by the cost point. So this is for me the most dominating. Here we see as well more brass, more bronze, and a little bit less the copper nickel silicon. But this is as well, depending now on how much current you actually want to go through these items. Okay, so if we think about copper, because we just talked about alloys, copper is as well something we should have an eye on. And in the first place, I would like to explain to you that, copper sorts, so the different copper versions, we would actually define in between something oxygen containing and oxygen free. So what's the problem with oxygen? If you look to the picture aside, you can imagine if you have some kind of copper oxide in the material, and somehow, maybe by processing at your site, let's say you have a welding process, and humidity somewhere around. And this humidity will actually get the hydrogen from the water into the base material, and it will make it very brittle. So in many applications, oxygen containing, which is, you can say, the most affordable one, is not wished. However, how do you then do it? You can actually deoxidize, let's say with phosphor, and the more phosphor you put in, the different kind of conductivities you achieve, because this is really a conductivity killer, phosphor. However, this is the typical oxygen-free versions which are in the market, and sometimes you need as well a lower conductive copper in order, let's say, to do a proper welding job. And if you do not want to have this and you really want to have something, the most conductive versions, then you go into the direction of non-deoxidized copper in vacuum. It's a little bit more effort. And coming up then later on with very conductive versions. Please note as well, especially when you think about hot dip tinning, oxygen-containing copper in the temper R360, so the hardest temper for copper, typically is not suitable for hot dip tinning. All the other tempers are. The reason behind is that the material will soften pretty fast and will not keep its temper. Good. Let's go to alloy maps, and I have made some effort actually in, let's say, getting the positioning of alloys a little bit more precise. And as such, you see in the first place the conductivity on the left side or right side, depending which unit you prefer. And we see below the mechanical properties, in this case, the tensile strength. I have made the boxes around the alloys according to the temper ranges from minimum to maximum, as well the ranges you might find in conductivity. So therefore, some box is a little thicker or the other one is a little thinner in gauge. And I think the key point in order to judge an alloy is you combine or you see the hardest temper. These are the big, thick spots. The smaller spots are the ones which are, let's say, other common tempers. And as such, you can draw a line between the hardest tempers and you get an idea what's, so to say, the limit of the first generation alloys, the solid solution, or how we call them as well, natural hardened copper alloys, ranging from copper to brass to bronze, and copper iron could be a precipitation hardened, but it's typically performed or processed like a first limit generation. If we go now, the hardening effect by grain, that's a potential. Maybe you have heard before about bronze materials able to make with super grain, as we call it, an extreme fine grain. With this effect, we can actually harden the material to about, for a bronze level, 100 to 150 megapascal, much stronger, even for a relatively soft version. And this is, you could say, the world of the copper natural hard materials, but there is another world, and this one is the one of the precipitation hard materials. And you can see here in this next map, these are the typical, you can say, high performance materials worldwide. I'm not listing here only Boway materials. You should have the possibility to have an overall look what is available in the market. And you can see three areas: the very conductive one, the medium, higher strength, and the extreme high strength, but typically low conductivity versions. And as you can see now, all the cages, the boxes, as well the little spots, you get an idea about the correct positioning of each alloy. And as an example here, you would see the 18150 or 18160 would be currently the leading edge when we come to high performance and high conductivity. And if we go to the copper nickel silicon alloys, especially the 70318, is a key, you can say, development of the last years. In automotive, there's a lot of 190.010, 190.05, 702.5. You see in these combinations, they are already lower on this set. Okay, good. But you have to think at least when selecting an alloy in 4 dimensions. So we just had the diagram with the tensile strength or yield strength and electrical conductivity, but you need to have in mind relaxation as well, forming. And when we go now to relaxation, you see the same chart as you saw the alloys before. And now I rank it by color mode. So you get an idea about which alloys you can use in the long term, not losing too much contact force, let's say over 1,000 hours, at different temperature levels. And there are quite some differences, ranging here from copper, magnesium, phosphor towards copper, chromium, zirconium, like the 18160, which you can stress up to 200 degrees C, 1,000 hours, and the other one would be just about 105. So there's a huge difference, and it's important to understand this. The graph has been here selected, allowing 20% thermal relaxation at a given initial load of 50% and based on relief annealed material. So if you do bending, and we take the same group, and you have to see now, for sure, if you do bending, in this case 90 degree R over T1, all these tempers are moving to the left side. So different graphs are available as well online to see what kind of bendability can be done per alloy. And as such, this is the CTW Alloy Advisor. We call it Corporate to Win. This is a web page we will develop in the future for many different kinds of applications for customer usage directly, which contains, in this case here, all the Boway solutions according to temper in a diagram, and you can select whatever you want on tensile, elongation, hardness, and so on. This page as well allows you to direct benchmark then the results in table form. And for example, here in a spider diagram, this one is a 7-dimensional selection. In future, we will add as well the metal value to it. And then you have a good selection in order to get the right answer for you. Even differentiating here between two different areas of stress relaxation, 105 and 150, getting you an idea about the performance of the alloy. So when we look at copper alloys, we can state we don't look just to tensile. We look actually, for example, to conductivity, to formability. This would be a result of a typical pure copper. So relaxation, just forget it. The metal cost I just put here as an incident to 100. And you can see the Young's modulus I cannot really influence. If I, however, go, for example, here to brass, you see the metal value goes down. Well, zinc is a really low-cost element. And you see I get a little bit more strength, but the forming as well is limited. It ranges from good to not so good. But again, brass is a low-cost material. If we go to bronze, you see I have a wide range actually on the Young's modulus. The metal costs go up because the tin is expensive. And else the relaxation performance already better than the other two. Nickel silver, this would need another dimension because nickel silver is typically the one very corrosion resistant. So if you think about your key of the door or the car key, very often this is nickel silver being used. So plating costs typically are not applicable. And if you think then about all the high performance materials, we would have the niche applications around it. So I just wanted to give you, we have limited time, unfortunately, today, a point on costing. Especially when we think about, what is cost? Typically people just talk about fab and metal price, but for sure, there's a lot of other costs. You have to think about scrap return, plating cost, logistical processing, qualification. But just to give you some idea, especially with this situation nowadays that all the companies are under pressure. We had in Innovation 423, we call it. It's a special Tomback, and it's a very special one because it contains, you can say, a standard Tomback combined with a nickel silicide. So something like a brass combined with a high performance material. And as such, no wonder we have this actually as a low cost replacement for tin bronze. This is running in large volumes already today in China, and it's getting more and more, let's say, attractiveness. Overall, the tempers are common like a bronze, but the conductivity is already double. But the key point all behind is the metal cost. And just to give you an idea, you see here the benchmark over, let's say, a 3-year period on copper tin 8, copper tin 6, copper tin 4, copper tin 5, and the 423. I just made you a calculation here just on LME, so not talking about premiums and so on, but you get an idea. 423 versus the standard bronze 6 is nearly $2,000 per ton just on the metal saving when looking at metal prices last week on London Metal Exchange. And this is something which is really remarkable. And with the metal increase we see nowadays, probably copper and tin and all these others will still go up. So something we might be interested in looking at. So positioning, as just mentioned, it's about the same in tempers. It's double the conductivity of a bronze 6. So that should be as well typically a no-brainer. And if we look to microstructure, in this case, we made the material directly with a super grain. So you see it here in the EBSD picture with texture. We are talking typically here about grain sizes in the area of 3 micron and below. And this leads as well to improved formability, including when forming very nice A spots for the electrical contact resistance, which is typically low than 2. That would be an application as well for press fit applications. So when benchmarking this against the bronze, you see now more or less the same tensile, the same yield, and the bending of this 423 is absolutely marvelous, much more fine even than the bronze due to the fine grain. And the key behind now is with the small little microstructure we have, plus small precipitates, we are getting at temperatures, you see here 125 degrees, at around 80% remaining force. At, that would be something maybe a copper nickel silicon is not even needed anymore. In order to make it more clear, you see here a direct benchmark versus copper nickel silicon 19010, so copper nickel 1.5 silicon versus the standard bronze versus the 423. And you can see if you go to temperatures, let's say here of 140 degrees, you would be at the bronze at about 60. We are still above 70. And with the copper nickel silicon, you're about 80. So maybe not every application requires a copper nickel silicon, and this would be a huge cost impact. However, for sure, if you think about recycling, this kind of chemistry, you have to recycle with us, because if you ask the standard scrap dealer, he will not know this alloy and give you not a good price. Okay, so I'm at the end now, and I have to say in general, alloy selection depends very clearly on the identification of the true application requirements. So it depends from application to application. That's why we have technical marketing, and we will support you around the world with that. For automotive, we have mainly high performance materials, and these are used very much driven by conductivities and relaxation. And please be aware as well, even to standard materials like a bronze, or even sometimes to a copper nickel silicon, there are meanwhile alloys which have been developed could be something able to cater this kind of cost pressure. Therefore, it's very important that we have this kind of information being across, you can say, the supply chain. Yeah, so this presentation, only a brief overview. If you want to get more infos, please contact me directly. We will plan in future, hopefully with the connector library, to do as well further videos, for example, on forming, on relaxation, plating, whatever. We have a large knowledge base here, and we are more than happy to share this in such kind of aspect. Thank you very much.